Hi, Assalamualaikum and a very good morning. So now we are in chapter 2, atomic structure. And now we're going to focus on the new subtopic, which is 2.2 quantum mechanical model, part 1 of the video. So in this video, we're going to learn on the definition of the term orbital. Also, we're going to state all the 4 quantum numbers of an electron in an orbital. So we have a principal quantum number n, an angular momentum quantum number L, the magnetic quantum number m, and also the electron spin quantum number s. So for the learning outcome of A and B, we're going to cover that in part 1 of the video, which is in this video. Meanwhile, for the learning outcome of C, we're going to look about that in the next video, which is part 2. So without any further ado, let us start with part 1 of the video first. So atomic orbital. So atomic orbital is basically a 3D region or three-dimensional region in space around the nucleus where there is a high probability of finding an electron. So ada kebarangkalian yang tinggi untuk kita berjumpa dengan elektron. So the nucleus is described as being surrounded by an electron cloud. So let's say here we have our electron in the middle, our nucleus in the middle, and the probability of finding an electron will lies in between this electron cloud. So the region here will have a high probability of finding an electron. So we are talking about the region, kawasan, okay? And outside of the region, it is very likely to see an electron or to find an electron. Okay, and for the orbital, it basically depends on their shape and also orientation. So we have the s orbital here, and then we also have a 2p orbital. So the 2p orbital will consist of 3 orientation, which is 2px, 2py, and 2pz. Also, we're going to have a 3d orbital. So the 3d orbital will have 5 orientation. So they have a 3d x square minus y square, they have 3d z square, they have 3d x square, xy, and then they have 3d xz and also 3d yz. So they're going to be 5 orientation altogether. Okay, and before we learn about the sketching, we need to learn about the N, L, M, S first, which is a quantum number. So we're going to look about that in this video. So atomic orbital, as mentioned, they are different in terms of their energy, their shape, and also the spatial orientation of the electron cloud. So the spatial orientation here refers to the orientation in space, which is in a three-dimensional region. So each electron here in an atom can be described and characterized by a set of 4 quantum numbers, namely a principal quantum number n, angular momentum quantum number L, magnetic quantum number m, and electron spin quantum number s. Similarly to us, each electron will have a unique set of n, L, m, and s. So each electron will have a unique set of n, L, m, and s, which is a quantum number. So we can relate that with our IC here, because each individual will have a different code or different digit for their IC. For example here, the first 6 letters here represent the year, month, and the day of born. Okay. Meanwhile, in the middle here, it refers to the location of where we are born. Okay. For example, if you are in Sabah, you will have a digit of 12. Meanwhile, this 3 digit here will be unique to each individual and it is a computer generated. And the last digit here, if it is an even number, then it's gonna be a female. If you have an odd number, then it's gonna be a male. So this situation, you can relate that with our electron quantum number. But for now, let us look into the principal quantum number first. So the principal quantum number n determines the energy of an orbital and thereby determine the energy of the electron in that particular orbital. And the principal quantum number can only have integer value. For example, n equals 1, 2, 3, so on up to until infinity. So let's say if we have these integers here, and then we label the shell as K, L, M, and N. So this one is up to you. You can see that the orbital size, for example, for the s orbital, keep on increasing when there is increasing in n number here. So what you can say is that when the number increases, the orbital size will also increases, which denotes that the energy will also increases. And this also tells that the electron will be further away from the center of the nucleus. And this one going to be closer. Okay. Next, we're going to have the angular momentum quantum number L. So angular momentum quantum number L will have a few alternative names. For example, they can also be known as a subsidiary, azimuthal, or orbital quantum number. And the value of L here indicates the shape of the orbital, the type of the orbital, and the angular momentum of the electron. And this value of L will be depending on the value of N that we have learned just now. So it needs to be an integer as well, which is 0, 1, 2, up to n minus 1. So the letters that we, for example, the numbers here can also be assigned as a letter. So let's say if I have a numerical value of 0, the subshell notation here going to be S, which refers to an orbital shape of spherical, which is like a circle here. But you can imagine it to be a 3D, which is a sphere. Okay, and then you have a numerical value of L, which is 1, and then the subcell notation going to be P. And this orbital here we're going to be looked as a dumbbell. So it's looking something like this. Okay, and then for the numerical value of 2, the subshell notation, which is in terms of letter, can be written in terms of letter D. And the orbital shape here going to be clover leaf. So clover leaf going to look something like this. Okay, so they're going to be 4 lobes altogether. And then for numerical value of 3, the subshell notation here is known as F, and the orbital shape here is, you don't have to know about that because it is out of our syllabus. So what you need to know is this 3 thing here, and also the numerical value as well as its subshell notation. So to further explain this part here, as I mentioned, it depends on the value of n. So let's say if your value of n is 3, then your L here can be 0, 1, and 2. Because it can 0, 1, and then 3 minus 1. So the one that you can get is 2. You cannot get 3 because the rule here need to be 3 minus 1. So you can only get 3 possible value. So if it is 3, 0, then it's going to be spherical shape. So it's going to be 3s. If it is 3, 1, then it's going to be written as 3p for the subshell. If it is 3, 2, 2 here going to be d. So it's going to be 3d. Okay. Now for the magnetic quantum number m. So magnetic quantum number will determine the orientation in space of the electron cloud surrounding the nucleus. So the possible value of m will depend on the value of L. Okay, so m here will equal to the negative L up to 0, and then it goes back to plus L here. Okay, so the example here, if L equal to 0, then m is equal to 0. Then if L is equal to 1, then m is equal to negative 1, 0, or plus 1. Because L here, you can substitute this negative 1, and then you will reach 0, and then you have plus L, which is plus 1. So you get 3 value, and then you're going to have 3 orbital in the p subshell. And then if your L is 2, then your m going to be negative 2, and then go nearer to 0, so -1, and then 0, and then +1, and then positive L, which is plus. So you're gonna have 5 orbital in the d subshell. Okay, so as what you have looked, N, you have learned about N, and then you learn about L, and now you learn about M. So L will depend on N, M will depend on the value of L. Okay, and now we're going to move on to the next part, which is S here. So electron spin quantum number, S. So for the value of S, it determines the direction of the spinning motion of an electron. So they can either be a clockwise or anti-clockwise direction, which is spinning on its own axis as what the Earth does. So the electron spin quantum number will has a value of positive half or negative half. So just as simple as that. Okay, now to understand more about how we can apply the value of N, L, M, and S, let us look into a table of quantum numbers. So our N here represents a principal quantum number, and our L here is an angular momentum quantum number, where L will be depending on the principal quantum number, and M here is a magnetic quantum number, in which it depends on the value of L, and our S here is an electron spin, where it can be plus half or minus half. And then we have our subshell, degenerate orbital, number of electron, and the total number of each electron. So now let us look into principal quantum number 1 first. So when n is equal to 1, then our L here going to be 1 minus 1, which is 0. And then since our L here is 0, then our M here will only have one value, which is 0 as well. And then for S here, it can be plus half or minus half. So in order to save space, I just put it as plus minus half here. Okay. And for the subshell, it will depends on these two values here, which is N and L. So 1, 0 will refers to 1s, because you know that the L value 0, 1, 2, 3, 0, 1, 2, and 3, and this is the letter. So for 0, the letter used is S. For 1, it's going to be P, 2 going to be D, and number 3 going to be F. So in this case, it's going to be 1, 0. So L0 here refers to S. So it's going to be 1s. Okay, and the number of the degenerate orbital will depends on M. So because we only have one digit, okay, so we're going to have one orbital. Okay, and then each orbital can fit 2 electrons. So since we have one orbital, then we're going to have 2 electrons, which is plus half and minus half here. Okay, and the total number of each electron in the principal quantum number of 1 going to be 2 here. Now we're going to look into n equal to 2. So when n equal to 2, we have two possible value of L, which is 0 and 2 minus 1, which is 1 here. So now let us look into here first, this row first. So when our L is 0, our M will become 0 as well. And then our S here will have plus and minus half. And then our subshell here going to be NL, which is 2, 0, which is 2s. And then the number of the degenerate orbital, because we have one value here, so it's going to be 1. And then because of having one orbital, then we're going to have 2 electrons in that orbital. Okay, now let us look into here. So since our n equal to 2, our L equal to 1, then our value of M going to be -1, 0, and +1. Okay, and then for the -1, we're going to have 2 electrons as well, which is plus half and minus half. Same goes to 0 here. So you're going to have plus half and minus half. And then same goes to the number 1 as well, plus half and minus half. And then your subshell here, 2L, which is 2, 1. So 1 refers to P. So it's going to become 2P. And the number of the degenerate orbital will depends on the value of m. So we're going to have 1, 2, and 3 value of m. So it's going to become 3 here. And the number of electron that can fit is 3 times 2, which is 6 electron. And hence, as a result, you're going to get 8 electron in total for the principal quantum number of 2. Okay, and later you're going to learn the orbital as 1s to be something like this, 2s going to be something like this, and 2p going to be something like this. Okay, and 1s can fit 2 electron, and that is why we have 2 electron here. 2s will have 2 electron as well. Meanwhile, 2p will have 3 orbital, right? Okay, so 1, 2, and 3, and then it's gonna have 6 electron in total, which is 6 here. And the total for the number 2 gonna be 8 electron in total. Okay, so you're gonna learn about this in the subtopic of 2.3. So this is a good heads up for you. Alright, now we're gonna look into the principal quantum number of 3. So you know that for principal quantum number of 3, the L here will have 0, 1, and 2. Okay, and then for M here, when L is equal to 2, then your M can be equal to -2, -1, 0, and then +1 and +2. And then for each orbital here, they're going to have +½ and -½, and same goes to each orbital here. And then the subcell here, because it is 3, 2, so it's going to become 3d, because N here is 3, right? L here is 2. Okay, this region here, 3, okay, sorry, 3, 2, then it's going to become 3d lah, alright? And then the number of the degenerate orbital will be depending on the number of m. So we're going to have 1, 2, 3, 4, 5. So we're going to have 5 orbital. And then as a result, we're going to have 10 electron in total. So the number of electrons in total for the principal quantum number of 3 will have 18. Okay. So now let us look into another example to help you visualize that. So for example number 1, we need to state whether or not each of the following symbol is an acceptable designation for an atomic orbital. We need to provide one set of quantum numbers for the accepted one. So we are given 4 questions here, which is 2D, 3P, 5D, and 7S. So all of these represent a subshell. Okay, and for a set of quantum number, we know that the quantum number need to contain N, L, M, and S. And for that reason, you can write it in terms of this way, which is the value can be A, B, C, or D, or you can write it one by one. Okay, right? So now let us do question A first. So we know that 2D here, from here you can know the principal quantum number. So the principal quantum number here is N is equal to 2. And then here's refers to an angular momentum quantum number, which is D. So you know that L 0, 1, 2, 3. When L is equal to 0, the letter going to be S. When L is equal to 1, going to be P, 2 going to be D, and L equal to 3 going to be F. So in this case, L here going to be 2. So as what you can see that N equal to 2, L equal to 2. Is it acceptable or not? Yes, it is not acceptable. So this is unacceptable. So you know that L gonna depends on the value of N. So L here need to be N minus 1. So the value that is acceptable gonna be 0 or 2 minus 1. Only these two values are acceptable. If 2, then it is not acceptable. So because of this reason, we cannot write the set of quantum number. Now we move on to question B, which is 3P. So from here, you know that N is equal to 3, and P here is equal to L equal to 1. So is this acceptable or not? Yes, they are acceptable because L here should be 0, 1, or 2. So they are choosing 1, so this is acceptable. And because of this reason, we can get our value of m. Okay, so m here, because this one is L equal to 1, so you know that our m value here can be in between 0, negative L, 0, and plus L. So I know that I can choose a value from negative 1, 0, and plus 1. Okay, so for this reason, I'm choosing m equal to plus 1. You can also choose s to be 0 or negative 1, doesn't matter. Okay, but you only select one of these value. And then for my s, I can select plus half or negative 1, either one of those. So in this case, I'm using negative half. Now for question C. So similar thing as before, you know that your n, your principal quantum number, going to be 5. And then your L here going to be equal to 2. So this is acceptable because you know that your L is supposed to be 0, 1, 2, 3, or 4. So 2 is acceptable. And because of this reason, our m value here can be either negative 2, negative 1, 0, plus 1, or plus 2. So you can choose any number. Okay, so for me, I will choose m is equal to negative 2. And then for s, again, you can choose plus half or negative half. Depends on yourself. So for me, I will choose s equal to plus half. All right. And then for question D, I know that n is equal to 7 and then L is equal to 0. So here is obviously acceptable. Okay. And since L is equal to 0, then my m going to be equal to 0 as well. And in my s here, I can choose negative half or plus half, but I only choose plus half here. Okay, so when the question asks for one set of quantum number, you only need to choose one of the allowed value. Do not write it all, okay? Because the question only asks one set of quantum numbers. Okay, so I think that's all for this video. See you again some other time. Bye.